Okay, in this tutorial video, we're going to look at how to do and work the operations for the Gravitational Force Gizmo Lab. In this video, we're going to take a look at the warm-up. So in other words, we're going to kind of learn the ins and outs of the various operations. And then we're also going to take a look at activity A, which is investigating gravity and mass to see what kind of connection, if any, there is between the two. Let's begin. In this student exploration for the Gravitational Force Gizmo, we're going to be looking at various concepts and vocabulary such as force, gravity, and vector. But before we do that, I want you to take a look at the prior knowledge questions that are written above. Read along with me, please. In the prompt, it says, on the night of a full moon, Mary decides to do an experiment with gravity. At midnight, she climbs up into her backyard treehouse, leans out the window, and holds an acorn as high as she can. She lets go and is disappointed to see the acorn plummet back to the earth. Number 1. Why did the acorn fall to the earth instead of rising up to the moon? Number 2. Give 2 reasons why Earth's gravity feels more strongly than the moon's gravity. At this point, pause the video, please, and respond to each of these prior knowledge questions. Okay, now that you've had a chance to respond to these prior knowledge questions, again, remember, prior knowledge questions are not necessarily right nor wrong. They just simply place an idea of where you stand on the concept. You know, do you have a firm grasp of the concept, or are you going to be sorting through misconceptions? Okay, either way, good learning is happening. So it's very important to acknowledge what our prior knowledge actually is. Let's take a look at the warm-up so we can see how the gizmo operates. Scroll down with me or go down on the page if you printed it out. Gizmo warm-up. From acorns to apples, gravity causes nearly every object to fall on Earth's surface. Gravity also causes the moon to orbit Earth and other planets to orbit the sun. The Gravitational Force Gizmo allows you to explore the factors that influence the strength of gravitational force. Here's what we're going to do. We're going to begin by turning on a box called Show Force Vector for objects A and B. You'll see that when you launch the gizmo, object A is on the left side of your screen and object B is on the right side. The arrow coming from each object are vectors, and that represent the gravitational force. The length of each vector is proportional to the force on each object, meaning the longer the vector, the stronger the gravitational force. The shorter the vector, the weaker the gravitational force. Let's take a look. So, as you can see, I've already launched the video, the gizmo. And we're going to click. If you look in the bottom right and the bottom left, you'll see a box that says Show Force Vector for Object A. Click it. Show Force Vector for Object B. Click it. Okay, now, in question 1, it says move Object A around. As Object A is moved, what do you notice about the direction of the 2 force vectors? Number 2, how do the length of the 2 vectors compare? And number 3, drag A closer to B. How does this change the gravitational force between the 2 objects? Well, as you can see, by turning on these force vectors, you can see that they point towards each other. That would be number 1. The other observation you should notice is that the length of each of these vectors are the same, which tells you the gravitational force coming and applied on each of these masses is also equal. The third question said to move object A closer to object B and observe. Notice as we move object A closer to B, the arrows get longer, which tells you the gravitational force got stronger. Now you can see the gravitational force is still pointing towards each object, still equal in magnitude, okay? But we can see that it got longer, which means the gravitational force got stronger. Take a few moments to respond to questions 1, 2, and 3 about these observations. Pause the video to complete your questions. Okay, now that you've had a chance to learn some of the basic factors involving this gizmo, let me show you a couple more before we begin. We're going to scroll or turn to the second page, Activity A, Gravity and Mass. Okay. So I not only can show a connecting line between the two masses, I can show the distance, which in this case is 40 meters. I can put a grid on here, which is very helpful. It tells me basically where the objects are. I can show force vectors like you saw earlier. I can even show what is called vector notation, which is written down in the bottom left and bottom right part of the screen. We'll be taking a look at vector notation in just a minute. But I want to show you how it is that you can turn on and off these functions. Let's take a look at the directions for Activity A. Turn on Show Vector Notation for each object. Check that the object's mass, MA and MB, is set to 10 times 10 to the 5 kilograms. Now, 10 times 10 to the 5 kilograms is really 1 million kilograms, but we're going to focus on changing the mass in terms of factors of 10. So from 10 to 20 to 30, okay? But it's going to be, as you can see, you have the ability to change it, right? We're going to make sure that both of them are set to 10 times 10 to the 5. Okay, I'm going to turn off those arrows as the directions say to turn on the vector notation for each mass. Okay. Question: how does the mass affect the strength of the gravitational force? Form hypothesis. How do you think the masses of objects A and B will affect the strength of the gravitational force between them? And number 2, this is a more specific prediction. How do you think the gravitational force between objects will change if the mass of the object is doubled? Pause the video now and take a second to form a hypothesis and a prediction based on the effect between mass and gravitational force. Okay, now that you've had a chance to make your prediction, let's actually take some data. Part 3. This is where we're going to measure and take some data. For measure, part 3, turn on Show Grid. Place object A on the x-axis at -20 and object B on the x-axis at 20. The Show Grid button is in the upper right-hand corner. Okay, so now we see both masses. We see the grid. We can see that object A is by default at -20, and we can see that object B by default is at 20. Now that we have the vector notation turned on, we can see that it is written kind of funny down below. So let's take a look at what this notation actually means. This notation will help you not only with your data, but will help you make some calculations along the way too. So let's make sense of this. If you read along with me, it says the force on object A is now 0.0417 I plus 0j newtons. The ij notation is simply a way of talking about which direction the vector is pointing. Okay, the force vector is pointing, in this case, the x direction. I stands for the x direction, j stands for the y direction. The x direction in this case would be east. The y direction would be north. So if you have a force that says 0.0417 I, well, that means you have a force of 0.0417 newtons pointed east in the x direction. And 0j means it's not pointing at all in the y direction. It's strictly horizontal. Okay, again, that means you have 0.0417 newtons in the x direction, which is east, and 0 newtons in the y direction. Okay, so we're not going to, let's not be too intimidated by this notation. Really, I just want you to look at the first number that is in front of I. Part A, what is the magnitude of the force on object A? Well, magnitude is what is the amount of force. It's how much force. It is the number written in front of I in the vector notation. It's also the number that you see after when you see force A in absolute value bars at the very bottom of the screen. FA is 0.0417 newtons, and FB is also 0.0417 newtons. That easily corresponds to what we saw in the warm-up when we saw that the arrows were identical in length, meaning they have the same amount of force. Remember, guys, the word magnitude means amount. How much force, right? How much force. And that number can be seen by whatever is in front of the I, or however much force is in the x direction. Now let's take a look at how to actually gather data. All the data we're going to gather is going to go in this column here. Okay, force factor, this column here, and MA times MB is this column here. Those are calculations, and we'll talk about those shortly. Now, we already see what happens when we have the first mass is 10 and the second mass is 10. The amount of force acting on object A is 0.0417, so let's record it. This one is already done. Now don't put a newtons in here. The unit of newtons is already here. Now what we're going to do is we're going to then in the next trial double the second mass and see how that affects the force on object A. Okay, so let's go to the second mass and let's change that 10 to a 20. And you can see the force on object A is now 0.0834. 0.0834 newtons. Okay, so that was what happened when we doubled just one mass. Now we're going to double both of them, right? So both of them are going to be 20. Go over to mass A and type in a 20. And you can see that the magnitude of force, the amount of force on A, is 0.1667 newtons, written at the bottom left-hand part of the screen. The last one is to keep this mass at 20 and triple the third mass. So when I say triple, I'm talking about with respect to the original 10 kilograms. So we've doubled the first mass from 10 to 20, and we've tripled the second mass from 10 to 30. Let's see how this affects things. You can see, ladies and gentlemen, that from doubling the first mass and tripling the second mass, the force, the magnitude of the force on object A is 0.2501 newtons. Now, here's how we can take a look at force factor, and here's what force factor means. Force factor means how much bigger is this force than the original force. So everything, force factor means compare the force to the original trial. The original trial had an amount of force of 0.0417 newtons on object A. Now if we look, the force factor on this would be 1 because this is the starting point and it's what we're comparing to. Now, here's how we can fill out the force factors. How does 0.0834 compare to 0.0417? Well, if you look carefully enough, you'll see that this is double. It's 2 times greater than this, which means this has a force factor of 2. Okay, so what does that mean? It means that if we double one mass, the amount of force acting on A has also doubled. That's what a force factor of 2 means. The amount of force has doubled. Okay, now if you look on this one, how does 0.1667 compare to this? And the easy way to tell, guys, is just take this number and divide it by the original number. See, if I take 0.0834 and divide it by 0.0417, I get 2. It tells you that 0.0834 is double the first force value. And so for each trial, take the new force and divide it by the original force. And we can see that when we do that, we get a force factor of 4. Now, hopefully this is starting to make a little more sense. Let's see. If I double the first mass, my force factor doubled. If I double both masses, well, what is that? It's double times double. What is 2 times 2? Oh yeah, it's 4 times bigger. In the last one, we doubled the first mass and tripled the second one. So take this value here, divide it by this value here, and you can see that it has gotten 6 times bigger. Okay, and again, the instructions for how to do force factor, if you didn't understand my video explanation, are written right here as well. Now, to complete the last column, here's what we're going to do. We're going to essentially multiply this mass times this mass. Now, when we do that, 10 times 10 is 100. Okay, I'm going to do the work down here, and then I'll simplify it up here. 100 times 10 to the. Now, some of you may not have learned what your rules for exponents are all about, but if I take 10 to the 5 times 10 to the 5, well, then I add the exponents. 5 plus 5 is 10. 10 to the 5 plus 10 to the 5 is actually 10 to the 10. And if I rewrite this with the decimal in the appropriate spot, then this is 1 times 10 to the 12. This is what we're going to write here. We're going to write all of them as 10 to the 12. I'm going to show you the first two, and hopefully I think you'll see the pattern. 1 times 10 to the 12. In the second trial, you're going 10 times 20, which is 200 now. 200 times 10 to the 10, but you have to move the decimal 2 places back, and we get 2 times 10 to the 12. Is there a pattern? I think there might be. So if this is 10 to the 12 and this is 10 to the 12, I wonder what we put here. Maybe it has something to do with your force factors right here. And indeed, if you did that, you would get 400 times 10 to the 10, which is 4 times 10 to the 12. Or you would get 600 times 10 to the 10, which is 6 times 10 to the 12. At this point, I want you to begin to complete the application, analysis, and conclusion and summary for Activity A. Do the best you can, and on Monday's class next week, we will go over the rest of this so that you can compare what you have. Ladies and gentlemen, have a great day.